is Sir ready for his cup of tea?
Yes, thank you, Jefferson. Very kind. How kind. Is everything okay there, Jefferson?
Just checking the lights, sir.
Ah, well, they look okay from here.
Indeed. Will that be all, sir?
Yes, fine, thank you.
As you are.
MrCrispin here once again, and welcome to my workshop. Today's video is mostly of turning in nature as I work away on the components required to create a collet chuck for the Harrison 190 lathe. Now the exact details of what that will look like will be coming up very shortly, but firstly a brief announcement. Just under 2 years ago, some of you will remember that I did a video tour of the UK's largest machining show called MACH, which is held at the NEC in Birmingham. It runs once every 2 years and it is shortly going to be coming up again. It will be running this year between the 15th and 19th of April, again at the NEC in Birmingham, and so for any of you who found that interesting, just a heads up, that is coming. Now, following the video I made last time, the organisers of the show have been in touch with me to offer me a VIP ticket and free parking, etc. So I shall be there, and for anyone who would actually like to register, I've put a link in the video description, and you're welcome to click on that and sign up, but only once this video is finished. On with the show. In a previous video I put together this ER40 collet chuck for the Myford lathe, and for reference that is what an ER40 collet looks like. Now, since putting that together I have used it a lot, and so bring your mind now to the Harrison 190, which is the grey machine I showed at the start of this video. I decided to try and come up with some kind of collet holding arrangement for it. Now, the standard collet type on a machine of that size is the 5C collet. These require slightly more apparatus to operate because you need the spindle nose portion, but then you also need the collet closer portion, which runs through the machine, and then by means of a lever on the end you go clunk and it locks the collet in or releases the collet. So more apparatus is required, and these are also pretty expensive. So I was talking to a friend of mine called Dave Ticehurst, and he said, well, seeing as you're already set up with this for the Myford, why don't you just create a way of holding ER40 collets on the Harrison, which sounded sensible. However, for lathes of this size, these aren't really considered a work holding option, so no one's really making a standard ER40 collet holder for the bigger spindles, this being a D16. So anyway, to cut a long story short, after a bit of rummaging around, I found this back plate. So that's a Bison back plate that fits the machine, and this is an ER40 collet chuck for a smaller machine. You can see there that is designed to go straight on to a I believe it's a D13 spindle nose, so similar design, cam lock, and that would go straight on. So what I've got to do here is make this fit on that. Now, because this is not a standard option, there is a few complications. First of all, the bolt holding pattern. If I was to pick these outer three, the bolts would break through in the actual bore of the spindle nose taper portion. So what I'm going to have to do is use the inner three, which are actually designed to hold the cam lock studs, but I've found some cap heads that fit in there, and very fine thread, but that will do the job, and I'll then be able to come through here and arrive in this clearance portion. So that's number one. Also, you will see that it is leaving the ends of the cam lock studs exposed. Is that a major problem? Not really, but I expect bits will get stuck in there, and in theory these bits are all supposed to be free. So these all have some slight clearance in them, such that the alignment's done by the taper and the face and not by these studs. So you could argue that as bits go down there, these will seize up. I think it's probably a rather academic argument, but while I'm doing this, I've decided what I'll do is to make a simple cover plate just to cover those ends. So in summary there, what I'm going to do is I'm going to machine this back plate to suit the inner of this, to hold it concentrically and in good alignment. I'm going to produce 3 holes that go through here to line up with these studs, and then I'm going to create a cover plate and probably shave a bit off the outer diameter where the material is not required. Now I thought perhaps I could get away with something simple, some kind of annulus I might already have to cover this, but unfortunately everything is not quite the right size. So what I'm going to do is use a piece of sheet aluminium and make it out of that. So let's begin at the lathe, and what I'm actually going to do first is I'm going to make this cover plate, and the reason for doing that first will become clear very shortly. Okay, that is locked on there. So this cover plate, how do I produce a annulus which has a inner of about that size where I've put the black line and an outer of roughly the width of the sheet? Well, the old-fashioned model engineering way of doing this would be to chain drill a series of holes all the way around, cut the inner out, then hacksaw and then file everything up at the end. Having done that method a few times, I shall reserve it for the eventuality of being stuck on a desert island with no equipment, because it's fairly tedious. A more regular method I'd use would be to do something like machine the front face of this and then put the fixing holes in ahead of time, and then use this as the fixture to machine the rest of it. So you put the holes in, fold it up, and then effectively use this as a fixture. However, what I'm actually going to do is use the Joe Piesinski method of pressure turning. So I'm going to rough this out on the bandsaw just on the outer profile, and then using this as a faceplate, I'm going to press with the tailstock against here to create friction, and with this rotating I'm going to use a trepanning tool to cut both the outer and the inner profile with no fixings required. So that's what I'm going to do. I will rough this out and then we'll have a go at it. Right, disc roughed out, and I'm now going to take a quick skim across this face. Okay, so what I'm now hoping to do is to bring the tailstock in and use it to position the workpiece. Got the centre in there, and I've got the centre punch mark that I used to mark it out. Okay, so that is the position that I want to hold it in. So I'm going to lock the tailstock up, and I'll see if I can just do this by hand. I'm going to retract the tailstock, and then I've found an appropriately sized workpiece or slug to support this. Okay, I think that's got it. So a bit of tailstock pressure on there. Lock the tailstock and see what happens when I start this up. Very touch slower perhaps. It's exactly as I thought. They were both faster. That's a bit more like it. Right, well that's worked for the outer, so now I'm going to move forward and trepan the annulus off. Any minute now. Well, thanks to Joe Piesinski, that was a rather efficient way of forming an annulus. Covering ring appropriately sized, I am now going to mark out 6 holes with which to screw it to the main body. Now I'll be using this as the template to spot through, so they don't have to be hugely precise. And to mark them out, I'm going to use the more traditional marking out technique. So I have scribed a line all the way around on the radius I want to use, and then to get 6 evenly spaced holes, all I need to do is set the dividers to the radius of this circle I've marked, and if I go around 6 times, that should give me 6 even spaces, which is just a little handy thing to know. So I'm going to pick a starting point, and from there I'm going to mark out, and 6. Right, I've now centre punched these, and I get 1, 2, 3, 4, 5, 6. So on to drilling. For holes above, say, 1/4 of an inch diameter, I'm a big recommender of clamping the workpiece down, particularly when the drill bit is going to break all the way through. For smaller holes like this, however, I'm quite happy to proceed by hand. Right, this can rest on its laurels for a few moments. Back to the main event, which is now machining this face to match this spindle nose. So as I said, it's a D13 spindle nose. That's a flat face and a tapered bore with an angle of 7.125 degrees. So somehow I need to set the top slide of this machine accurately to 7.125. When I did the video setting a tool post grinder, I showed a Joe Piesinski method, there's his name again, which was to use the tailstock and use a digital readout. If you want to see how that actually works, either look at my video how to set a tool post grinder or have a look at Joe Piesinski's channel. What I'm going to do today is demonstrate a different method, which is to use a sine bar. Now I'll leave you to compare and contrast the methods yourselves. I will just say this one involves a little bit more of a three-handed operation, but what I've got here is a 5-inch sine bar, the appropriate size slip gauge stack to make a 7.125 angle, and then because I'm clocking along this way, I need something to transfer the angle 90 degrees, so I've got this block which has another face here. So I'm going to attempt to stick this to the face plate. Okay, piece of wood is just there as a disaster saver. Right, so these are carbide slip gauges which aren't magnetic, which is handy, and they are in there nicely, and with a feeler gauge I can check that's in contact. So I'm happy that that is correctly set up. So all I need to do now is mount a dial indicator on here and tram it in to this edge. Five, 6, 7.125, I think. This is a 2 micron indicator. Okay, so it's falling away. A few goes later. Final confirmation says I'm within about 15 microns over that length, and considering the length I'll be actually turning is 3 or 4 mil, that will be perfectly adequate. As for which method is preferable, this one or the tailstop method, I'll let you decide. You can let me know your thoughts. One thing we can all agree on, however, is that the quickest way to disassemble this setup would be to turn the lathe on. But please only try that if you're capable of catching 4 things at once. As for myself, who never made much of a fielder, I'm going to go with the demagnetization option. To begin machining, I'm just going to rough out a square boss that's slightly bigger than this diameter. Roughing has been carried out and the piece is now at most of its finished dimensions. The OD is just sized so I can get a grip of it, but nothing excessive. This face has been brought back to leave me about 1 millimeter before the studs bottom out, and this diameter here has been taken to match the extreme diameter of this taper. So really the only remaining thing to do now is to actually machine the taper on here such that the whole thing comes backwards and meets snugly with the face. However, there's one important thing to point out, and that is the presence of this corner radius. Clearly the turning tool's nose radius has been transferred into the corner radius here, and if I was to proceed and just machine a taper, I would end up with that radius being present, and that would cause a problem because this has no clearance at all. It's a taper, face and the sharp corner. So before I actually go as far as sizing the taper, I'm going to dig a bit out of this inner and create some clearance so that there's no fouling geometry. And to do that, I'm just going to come back in with the trepanning tool I used earlier, come down this face, dig the radius out and probably create a little clearance groove, maybe 0.1 or 0.2 of a millimeter deep. Now as it stands, I've got just over 2 millimeters. Okay, so I showed I have just over 2 millimeters in the longitudinal direction of clearance that needs to be closed. Now you might think that you could somehow use trigonometry to find out how far I would have to wind this in order to close a 2 mil gap that way. Well, actually, A, there's no need, and B, it's more accurate if I don't. My preferred method when doing this kind of thing is to zero the carriage position whilst doing the cutting with this axis, which is what I did. So the carriage was zeroed, and now having taken that measurement, I know that to get this to the finished size, all that has to happen is the whole carriage needs to move 2 millimeters. This does not change, no cross slide adjustment. I just move the carriage the required distance and then wind along the taper angle. Just finishing off there with an oil stone, because a turned surface in cast iron, particularly with the sintered carbide bits, quite often leaves you a surface that's slightly undulated, and when you're looking for a good contact, I find a stone just takes those off and allows you to be a little more precise in the fit. Okay, I've been working away using the same longitudinal feeding technique, and that looks like it's about there. Now, crucial point with this, as turned, you want a very small gap between the two faces, and this 1/1000 feeler is just sliding in there, so I'm going to stop at that for camera purposes. There you are, you can see the 1/1000 feeler. The idea being there that once those screws draw the piece on, it forces the tapers together and both confirms concentricity and also gives the work holding arrangement slightly more robustness in the radial direction. Okay, so that is turned. I'm not going to bother at this stage with all the chamfers etc. I'll do that at the very end. So I will now take this off and do the various drilling operations. I will say one thing, and that is it's a good job that spindle bore isn't any bigger, or that would have jeopardised this whole operation. Having taken the back plate off the lathe, I have removed the studs, and now I've got it and the rear portion of the collet chuck clamped down to this box plate. I'm going to spot through the clearance holes for these 3 bolts, and then I will spot through the holes for the ring. After all that, it is time to put all the pieces together. Just pulling in on the taper now. Okay, so that has pulled that tight up. Of course, I managed to lose my pen mark. They look pretty similar. Wherever I go. But that one looks the best. Two tasks remain. One is to turn a bit of a chamfer on this corner here, and the second is to adjust the chuck to get it running true. All sharp edges have been removed, and that's finished. So just to clock this in. Now, to begin with, I'm going to take these grub screws and just bring them in so they're making contact with the inner diameter, and I'm just going to back these off such that there's just a small amount of friction. Right, well, that's not a bad start of a 10. So working in pairs, that is the high spot, so I want to slacken that side, and then that was the opposite of what I was expecting. That is 30, and that is 20. Zero, 20, and let's go down a touch, 10, 14. Let's now move over to another side before it to right, well, if I can snug them up and keep that, I'll be happy. Keep going, looking for the highest point and nip that. Right, well, that's fully snug, and 2 or 3 microns worth of run out, which I'll take. Let's put this in a low gear. So all said and done, that is running within about 2 microns. Now the acid test, let's put a collet in there and measure some more runouts. Reading number 1 at the collet end. That is roughly 5 microns, if not 4 microns. Very good. Reading number 2 at the opposite end. Either the clock's broken or that's very good. Well, I think that's about the least run out I've ever measured on anything. So that's highly satisfactory. Right, I will spare you the repeatability test where I take the whole thing off, put it back on 10 times, but as I go forward with machining projects I will keep you up to date with the performance of this arrangement. So that is that for another episode. That's another collet chuck ready for action. In my next video I will be returning as promised to the locomotive, and I'm looking forward to starting work on that again. For those of you who would like to attend MACH, the link's in the description, and apart from that I'll say thank you for watching. I hope you found this interesting and see you on the next video.